All right, class. Yesterday I had technical difficulties with the electronics. So what I'm going to do is I'm going to re-record pretty much the lecture that we did on, was it January 6th? I think it's January 6th here. So 1.8. Let's go with it together here. It's called combination of functions. So that's one thing we're going to do, combination of functions. All right, next thing we're going to do is called the composition of functions. Okay, so two things in our mind. Let's jam with it here. So first things first, and this is going to be notation. So real quick here, talk to me about what is the operations? What are the four operations we can do with numbers? And so hopefully you guys remember, we can add things together, we can subtract things, we can multiply things, and we can divide things. Well, actually not things, but numbers, right? So those are your four operations of numbers. This is exactly what we want to do here. We want to do it now in terms of functions. So combinations, because there's multiple ones. So let's do this here. Let's add, subtract, multiply, divide functions. And then we'll kind of get into why is it important a little bit as well. So let's jam. So first things first is, let me give you notation. So let's go with addition. The addition notation for functions. And so if you have two different functions, we'll call it f and g. So f plus g looks like this. That is one way that we write that we want these two functions to be added together. Another way we write it is like this, f plus g in parentheses, and the x is what we want to do. So that x represents the variable that we're using. Okay, and there's a third way. So you'll see it all three different ways. This one is more like how we do the operation. This is more like how we going to work it out right there. So I could write f plus g and just kind of leave it just like that. I can write f plus g in parentheses of x. So I'm adding these two functions together. X is the variable. This one means f of x, f function plus the g function. Let's jam some more here. Let's go subtraction. So subtracting two functions together, you're going to see it. That's going to look very similar here. F minus g, or in parentheses, f minus g of x, if you want to tell what the variable is, or you can say f of x minus g of x. Boom, done. Multiplication, let's go, or we still say product. We can say product, but it really is just multiplication. All right, to do that, all we do is we just put f and g, we put them close together, and that's it. Just like we do multiplication of like x times 5 or something, or 5x, or x times y. We do the same thing here. This is fg, no space, no nothing. You just write the letters close together. And so next one, fg, naming the variable called x this time, or f of x. And this time I do need to put like a little dot. I'm going to put my little multiplication dot between the two. And there's that. All right, I'm going to have to try to squeeze division into here. Division. Okay, here we go. F over g. Hey, this is just like a fraction bar. It's just, we call it a quotient, technically, quotient or division. So f divided by g. We could say f divided by g of x, that's fine too. Or individually, we could say f of x on top and g of x on the bottom. Now, these variables, or these names of these functions, are, we say they're arbitrary, right? So I could write m plus n, and those would be like two different functions, right? Or in business, sometimes we say revenue. I could put r minus c, called revenue minus cost. That's what that is. Or I can even go the other way. I don't have to add f plus g together. I could just actually be doing g plus f because I want to add that way, or I want to subtract that way. So the naming of the functions isn't as important as making sure which function is which. So let's do that here. Let's jump to our first example, and then we can go into what's important, why they're important. So exercise number 1. So It says given, and let's go f of x. F of x is 2x plus 1, and g of x is, and let's go with x squared plus 2x minus 1. And so let's go with, let's go a. A is going to be, let's add these two functions together. And I'm going to use this notation right here. Let's add these two functions. What else can I do this? I can subtract these two functions real quick here. I'll let you guys do that one. And then I'm going to do this. I'm going to subtract G or F from G. That's why I can turn these around anytime I like, because I'm just trying to figure out which one I want to do. That's all. And so all yours. If you want to try it yourself first, go for it. If you want to wait for me, then we'll do it together. All right, let me start here. So if you notice on the previous slide, I can write it like this. I can write it as f of x plus g of x. All right, and if that is the case, what I do is I just labeled f of x and g of x. So what I'm going to write down the function themselves. So it's actually looking up here, knowing what the function is. It's 2x plus 1 plus sign right here coming around. And then the g of x. G of x is this guy over here. G of x is x squared plus 2x minus 1. So what I'm going to do, I'm going to add that together. So normally we like to add polynomials by looking at the highest exponent first. This would be x squared. Let me erase a few things here so it doesn't get all overwhelming here. And then let's look for common terms or like terms. 2x plus 2x makes 4x. And 1 minus 1 actually cancel themselves out. So just left with x squared plus 4x. So that's it. We've added two functions together. We've created a third function, totally different than the previous ones, but it's the addition of those two functions. Okay, let's subtract these guys. So all yours, if you can go ahead of me now, do it. All right. I'm going to try this one now. So f of x minus g of x. Again, same thing applies here. We were left with 2x plus 1 in front, minus sign this time, x squared plus 2x minus 1. Okay, in this case, we do have to, at least what I like to do, either distribute the negative into each one of these guys or just drop the parentheses. I like dropping the parentheses. It's much cleaner. So this little negative does have to be multiplied in. So negative x squared, negative x, 2x, sorry, and then a negative times a negative is a positive. Okay, collecting like terms as we do it. There's my negative x squared, the only x squared there. Oh, and this time the x's are gone. 2x minus 2x, those are gone. But 1 plus 1 makes 2. So there it is. The subtraction of these two functions is negative x squared plus 2. Okay, going the other way. I could say what I really want to do is subtract actually f from g. I want to do that. And let's see if it turns out to be the same thing or different. Let's check this out. So there's g of x here minus f of x. That's what the notation says. And the g of x is going to be x squared plus 2x minus 1 minus f of x was 2x plus 1. And finish it off if you can. Go for it. I'm going to drop the parentheses like I did last time. And then we're going to drop parentheses by distributing the negative. So negative 2x, negative 1. And final answer, let's go with it here. So this would be x squared. And again, you can slow me down. You can slow me down by the speed of the video. That's fine. That's one way to do it. Or you could just pause me anytime. So I'm not in class, so I'm not waiting for students to be done. So this is a slightly different lecture here. And so please do pause me if you need to anytime, just to sort of catch up. Okay, so there's my 2x, negative 2x. These guys have to go away. And I'm left with a negative 1, so negative 2. Okay, so notice those two are a little bit different from each other. Is that right? In fact, they technically are opposites. That's what they are. But we didn't get the same answer. Subtracting one number from another is different. Just like remember in in pre-algebra, I guess, if I did this here, if I did 12 minus 5, I would get a 7, right? If I flip the numbers around, 5 minus 12, I would get a negative 7. Well, the same thing happens with functions. These guys are opposites of each other right there, but they are different. All right, before we go on, let's do this here. Why is this important? So important, I think so, in the fact that if you were to add two functions together and get a different function, it gives you information. It actually gives you more information than you knew before. That's why it's so important. So maybe a quick little scenario here. How about if we were at a car dealership, auto dealership, and we were selling stuff, and so what we found is the manager that kept track of how many car sales were. He kept track of all the car sales, and let's just label it as C, right? And then you had another person that was tracking all the just the automobiles only, right? Let's say this here. Let's say automobiles, so cars and trucks. Let's say this company sells cars and trucks, automobiles and trucks. So total, I sorry, messed up on here just for a little bit here. Let me do this here because this will be a little bit better scenario here. um, total sales. Let's say a person knew manager that's in charge of the dealership, he always recorded total sales for the month. And let's say another manager, he was very diligent and he recorded all the car sales, and cars meaning the small cars in there. And then there was also a truck division, and the guy that did the trucks, he did not pay attention too much to his sales. So what we do is we know the total. We know the total number of cars that were sold during the month. We also know the total number of cars that were sold during the month. So the question is, can I figure out how many trucks were sold just by adding or subtracting? Absolutely. I can just do this here. I can figure out what the total number of cars were. I subtract the total number of cars and I get the total number of trucks. So notice, just by subtracting, what I've been able to do is I've been able to gain new information that I did not have previously. I didn't have how much total car sales there were. So that's the same thing that happens with functions. Functions do the same, maybe just a higher level one here. Um, I saw this chart, which I thought that was really, really cool. I should find it. I found it in a magazine. This person, he did a chart of how much people got paid. So wages, annual wages, and then he also tracked so per year. So like in 1900, 1901, 1902, and he did it all the way up to the year 2000. He tracked what was the average annual wages due, and you could look it up by taxes, tax returns. Okay, and then he did this. He did the taxes that they paid during the year. So annual wages and taxes that they paid. And so what he did is he decided, I'm going to subtract these two. So what is annual wages subtract taxes of the U.S.? And dun da da da, it's called spendable income. So something we did not know before, but now spendable income. And it was pretty cool. The graph kind of went like this. The graph was wages like this, like that. And then the taxes were like this. So some years it was it was not always the same per year, right? See this little gap right here, that was the difference between, or that was the spendable income, which I thought that was pretty cool. Okay, so again, something you did not know before, you were able to get by just by subtraction. You could do it by addition. You could do it by multiplication. You could do it by dividing. Just to maybe a little quick note here, when I was in college, one of my professors, he was good friends with the accountant for Nike shoes, and this accountant, as they were talking, he said that Nike shoes, what they do is they figure this out right here. They figure out actually what's the spendable income per zip code. So slow zip code. There's two of them here, I think. So they would figure out the zip codes in the area, and they would figure out how much spendable income people have in the area. And based upon that, they would actually will sell the shoes, or they'll price the shoes out for that particular zip code. And again, it's the same thing here. You're just subtracting. You're finding more information that you did not know before. So I thought that was cool. Okay, so that's the importance of it. It's useful to get information you did not know. Okay, let's go with something else here. Let's go with finding domain. So I think we're on example number 2. Find the domain of quotients of functions here. So we haven't done multiplication. I figured multiplication was kind of easy here, but I'll let you guys try it first. I think we just do 1 here. So let's do this here. I'm going to set up a little function here. Let's see, f of x. I'm going to go with f of x is equal to x plus 2, and then g of x is equal to, yeah, let's do that here. Let's do 4 minus x squared. Okay, I'm going to change it up on you just a little bit here in the beginning. Let's try it. I'm going to find out this here. I want to find out what is g over f. So first of all, tell me this. That's part A. Part B is find the domain of g over f. So I'm kind of messing with you here. Instead of putting the f on top, I put the g on top, just for us to sort of think things through here. All right, so let's go with it here. So this means that the g function goes on top, the f function goes on the bottom, and the g function is the square root of 4 minus x squared. That's cool. The bottom function is x plus 2. Okay, what do we need to know? What we need to know about domain, and we talked about it earlier. Domain is, we have domain, two things that are a problem for us for domain is whenever we have fractions, we can't have a 0 in the bottom of our fraction. Another problem for domain is any square roots, because the square roots here have to be either 0 or greater than 0. So it has to be greater than or equal to 0 right there. There's your two domain problems. So if you look at this here, we actually have both of them. Oh, you know what? Sorry, let me do this here. I didn't want to do that. I want to just go x. That's it, just x right over here. So let me erase the x squared. Okay, so let's do this here. So first things first is we have both of those problems. Notice on the bottom, I could get a 0 on the bottom there. And this one's a square root function, so that means I have to figure out when is this guy going to be greater than or equal to 0. I got two things that are happening. So real quick here, A is done already, right? A is done. This finished up A right there, just as soon as that was done. So here's the answer for A. But now let's take a look at domain. So first things first is the bottom, x plus 3 or x plus 2. What we want to do is we want to figure, when does this give you a 0? It gives you a 0 at x equals -2. Perfect. So that is one domain issue we have. And in fact, what's happening here is that I should actually not circle that one. I should say x cannot equal -2. That's one issue we're having. Now from the top problem is the square root problem. So whenever you have a square root, all we do is we just put the stuff that's inside the square root and we say that piece has to be greater than or equal to 0. And then we start solving. So hopefully we can solve this. Subtract 4, subtract 4. Divide through by -1. And then remember, if whenever we divide through by negative or a negative number with inequalities, we have to switch the sign. So there it is. The domain of this function is the fact that x cannot be equal to -2, and also that x has to be less than or equal to 4. Well, don't you see that if x is equal to 4 or less than or equal to 4, x has to be less than 4 in order for this to work, right? But as you go along this line here, notice you are going to run into -2 sometime. All right, so here's the way we write it. Two different ways to write it. We can say this here. We can say the domain of g over f, and you can write g over f of x if you like, is x less than or equal to 4 and x does not equal to -2. That's one way of writing it. And then another way to write it is by interval notation. So we think to ourselves, look, if I start off all the way from -infinity, so I keep on going, I'm going to run into -2 here. So the other way to write it is to go like this. All the numbers work from -infinity up to -2. And right at -2, there's a little break. That little -2 is a problem area for us. So we go like this, and then we start off again after -2, and we go up to 4. And we're going to include the 4 as we did in our appendix chapter when we started class here. The bracket is because we're including the 4 in our answer. All right, and now we move on to something called the composition of functions here. Let's do an explanation first. Let's do this. Okay, so maybe let's go. We're going to go buy ourselves a laptop. That's what we're going to do. And what we do is we have some discounts on the laptop. It is a $1,000 laptop, which is kind of cool. We have it's instant $300 off instantly. And then what happens, it's another 10% off of the sale price. Okay, let's talk to me. Talk to me here. What would be the price for our computer? Well, notice kind of there's two things happening here, right? First of all, there's the $300 off. That's what happens first. And then there's a second function there. So there's two different things being done to that $1,000. So first things first is $1,000 being subtracted by 300, making it 700 right away, right? That's the first step that happens. Then we take the $700. So let's go first step, second step. And then we're going to take 10% off from the 700. So what's 10% of 700? 10% of 700 would be 70, right? So then we subtract those guys. So 700 minus 70 gets you 630. Okay, so our $1,000 laptop, we get to take it home before taxes at 630 bucks. But this is what the composition of functions is all about, is that we're trying to create a function that does both of these together. So instead of having to do one and then the other, and having it to do two different things we do, composition sort of combines this together. All right, another way of looking at it, kind of a little more abstract here in mathematics, is let's say this is our x values, right? So let's say 5, let's see, 6 and 7, right? And let's say this function here, what g function does, it adds 3 to each of these numbers. And so there's that. That's cool. So this is x. This is going to be g of x. And there's an f function right over here. And what the f function does, it always doubles whatever you have. So the g function adds 3. The f function doubles it. So let's go with it here. So 5 adding 3 would make an 8. 6 adding 3 would make a 9. 7 adding 3 would make a 10. That's cool. That's our g function acting. Okay, then this one's going to double everything here. So then this 8 turns into a 16. The 9 turns into an 18, and this turns into a 20. We good. So notice there's 2 functions being added. All right, now what we want to do though is we want to combine those 2 functions so we don't have to do one thing, get numbers for it, and then do the next thing. We want to just do it all at once. Okay, so there it is. So let's jam. This is the composition of functions. Okay, some notation. We got to do the notation stuff. So here's what we do. We say this. We say f, and then this one's kind of funny. This one's an open dot like this. So open dot. Oh, we can write it all the different ways we wrote it earlier here. So we just write FOG. So sometimes we just pronounce it as fog, but it's really F composed with G. That's what this means. All right, we can write it like this. We can write it with the variable in mind, like we wrote the other stuff. Boom, boom, boom. All right, and we can write what it really means as far as an operation is concerned. This is what it means. We're writing the F function, then the G function. So the G function, we call it as inside the F function. It's nestled in there. Or if you think about it as like an onion, right? F is the outside layer, G is the inside layer. So we want to be able to compose these things. So let's go with it. This is exercise 3, I believe. So given f of x is equal to x plus 2. So notice what this guy does. It adds 2 to the function. G of x, what g of x does, a little bit more complicated. It squares something and subtracts that from 4. Okay, what we want to do is we want to compose these guys. So I'm going to take f, compose with g. All yours to do that, exactly what we've been doing before. We figure out, well, if that's the case, then what we are really trying to do is this right here, according to our definition. And what we really are trying to do is this right here. We're trying to nestle the g function inside the f function. And so here's what we do. We take this function. This function is nested inside the f function. So normally what we say is we say, okay, if g function is 4 minus x squared, that's our g function right there. It came in. It's now our new g function. And then we're going to try to put it into the f function. Well, the f function, what it does, it takes whatever you have and then just adds 2. That's what it does. So let's do this here. So any x now changes into what you had for g. So what we had for g plus 2. And of course we simplify. So let's get rid of all the parentheses. And let's simplify that to the negative x squared plus 6. Okay, so just like the other functions, we could go backwards. So how about this? I want to find g composed with f. So all yours for that. So it's kind of going the other way. That's all. Okay, 30 seconds. Let you guys try it yourself. Go. All right, that was 30 seconds. G of f of x. So G composed with f, or G is the outside function. F is now the inside function. Now let's see how this is going to work. So what is my f function? My f function is x plus 2. Perfect. So here's what I'm going to do. I'm going to plug that into, I'm going to put my little letter here. I'm going to put that into here. So the g function, what it does a 4 minus, but then this guy now becomes x plus 2 to the, and it's also squared still, right? Ooh, so we have some work ahead of us. We have to simplify that out. And so we're going to go with 4 minus, let's see, x plus 2 off to the side. If you need to, do it off to the side. Just kind of go x plus 2, do another x plus 2, and see what you get real quickly here. That'll be x squared. 2x makes 4x plus 4. There it is. Again, pause the video if you need to go a little slower here. So x plus 2 to the second now becomes x squared plus 4x plus 4. And now what we do is we get rid of our parentheses. And then we cancel off things that are like terms. In fact, they're opposites of each other. Done. Negative x squared minus 4x. That is the composition of G with F, or the composition of G to F. All right, composition is kind of funny too, because you can compose function with itself. So let's see this here. Let's go with C. C, I want to do this. You guys find me this. What is F composed with F? So remember the F function. The F function is x plus 2. Right there. And there's my F function from the previous slide. And so this means F composed with f of x, which means f of x. So it's almost, you're doing f of x twice. So let's go for it here. So what is f of x? F of x is x plus 2. So that's the inside. That little inner f of x changes into x plus 2. All right, and then now we do the outside f of x. So this little piece here, x plus 2, replaces this little x right there. So answer is x plus 2 plus 2. Are we good? So this little x plus 2 got in there. All right, drop parentheses, add it together, and we get ourselves x plus 4. Hold on, here it is. Look at this. This is what should make sense now here. We did f of x twice, right? We did an outside function and an inside function. What does f of x do? If it takes a number, right, it adds 2 to it. That's what it does. Well, if you did f of x once, and then you did the same thing again, notice what happens. Just taking a number and now adding 4 to it. So it's doing the same function twice, in a sense. But we're not doing like plus 2 and then another plus 2. We're more sophisticated than that. What we did is we just added 4, and it combined both functions together. That's what we got. That's the important part with composition of functions here. So let's go back to our computer example. Our computer example was a $1,000 computer. It was $300 off. Let's see if we can make some functions here. So this was the first function that we did, right? So this is the inside function. The first function that you do is the inside function. What happened here? You had to take whatever your computer was, and you subtracted 300 from it. Boom, first function. The second function was getting rid of 10%. Now this one is kind of a bit of a tricky one. This one says this, whatever you're selling the computer for, we're going to take away 10% of that computer price. So there's my second function. Okay, hopefully that makes sense because we're just kind of putting a few things together here, and email me if it doesn't. Okay, so first thing is the $300 off. Got that. Okay, and then the second thing is 10% off. I got that. There's my two functions here. So what I want to do is I want to create a function. Instead of doing two things here, taking the $300 off, then doing that, I want to create one single function that does both of these things. So let's go for it here. So I'm going to do this here. I have to compose F with G. So notice F is the outside function. F on the outside, G on the inside. Okay, then this one's a little bit tricky as well. This is going a little bit beyond the textbook here, but it's good to do that here. So the G function, what is that? That is the X minus 300. Ooh, look at this. Notice the F function. Notice the F function actually has two different X's. One is for the original price, and one is for the 10% off price. So what we're going to do is we're going to plug in the X minus 300 into both of them. So let's see how this works. This is going to go with X minus 300, which is what I just did right here. This is that one right there, minus 0.10% of X minus 300. That's this piece right here. So I had to plug in two different X's to make them X minus 300s. Okay, let's do this here. I think we can do this real quickly here. X minus 300. You're going to distribute that little negative or 0.1. So this would be negative 0.1x. Okay, and then you go over here. This would be a negative times the negative is a positive. And then 0.1 times 300 is 30. Check me on that if you need to. Okay, then I have a 1 here, and I have subtracting 0.1. So that I know would be 0.9x. Negative 300 plus 30 makes a negative 270. So I have this little function called f of g of x, which is equal to 0.9x minus 270. So my question to you is this. Oops. What is f composed with g of 1,000? So if you were to plug 1,000 into that, what would you get? Let's go with it here. So 0.9 times 1,000 minus 270 gets you, so 0.9 times 1,000 is 900, and 900 minus 270 gets you 630. Dun, da, da, da. That's it. That is how cool it is. So we made a function that does the work of both functions at the same time. And it happens quite a bit in the real world, especially if you're programming things. Let's see, computer programming. You're making the robot go to the left for 12 paces. Then you want to turn and then go to the right 6 paces. Again, that's two different functions here. One goes one direction, the other one goes another direction, and you could program it by this means here. So the $630 is the same thing that we got over here, the $630. Okay, so we are done. We're almost done with 1.8. There's a few little things that we didn't cover, but I think for the most part, you guys should be able to get it. I'll let you guys try it on the homework as well. So wish you well. I'm glad I was able to redo the recording of the class here for you. And have a good day.